Yeah, just click got it. Okay, and now start with the initial value problems of in the differential equation. Yeah, first I will give you what the short example for introduction for just reviewing the material that you maybe got haven't gotten before. Yeah, using the brief subject. Yeah, previous subject using exact solution, and then I will also give you the second one is by using numerical computing in the numerical computing problems, and I'll give you also the more as a simple example and as well as the complex example, but not in detail. Yeah, okay. Because this is not including for using the test for next programs. Okay, what's on here? Get here. Okay. This one. So, okay, the cell position. So the position. Okay. Yeah, that. So to show the sound. Yeah. Sound. Cell sound. Sound.
Talk about how to solve the initial value problem as it relates to differential equations. So let's start with this example problem. First, let me adjust the size on this. So let's say that dy over dx is equal to 6x minus 3. And we're given the point y of 0 is equal to 4.
But you now the rolling call first for using the chatting room. Ready. No, because we'll be ready for this one. Type the ready in your chat room. Okay, after ready, and then we'll get continue.
So let's start with this example problem. First, let me adjust the size on this. So let's say that dy over dx is equal to 6x minus 3. And we're given the point y of 0 is equal to 4. So this means that x is 0 and y is 4. How can we solve this differential equation? The first thing I'm going to do is multiply both sides by dx. So I have dy is equal to 6x minus 3 times dx. So I like to separate the variables. I like to separate y from x. Once the variables are separated, we can integrate both sides. So the integral of dy is simply y. The antiderivative of x, or x to the first power, is x squared over 2 times the constant that was in front of it, which is 6. The antiderivative of a constant is just that constant times x. And of course, we need our constant of integration, c. So this right here is the general solution to the differential equation. But now, we need to plug in our initial value. And the reason why we're going to do that is so that we can find the value of c. So we said that y is 4, 6 divided by 2 is 3, x is 0, and so 0 squared times 3 is 0, so all of this is 0. We can clearly see that c is equal to 4. Now the last thing we need to do is plug in the value of c. So our final answer is going to be 3x squared minus 3x plus 4. So this is the solution to the initial value problem. Now let's move on to our next example. So let's say that dy over dx is equal to 2xy. And let's use the initial value, y of 0 is equal to, let's say, 2. Go ahead and work on that. Actually, let's make that 3. Now once again, let's separate the variables. But first, let's multiply both sides by dx. So we have dy is equal to 2xy times dx. Now the next thing that I'm going to do is divide both sides by y. So on the left I have 1 over y dy. On the right, 2x dx. So all of the variables have been separated. We have the y variables on the left side, the x variables on the right side. Now the next thing that we need to do is find the antiderivative of both expressions. The antiderivative of 1 over y is the natural log of y. That's one of those things you need to know. The antiderivative of x is going to be x squared over 2, and then plus the constant of integration. So canceling the 2, we have ln y is equal to x squared plus c. Now, what do you think we need to do at this point? What we need to do is place both sides of this equation on the exponent of e. So we're going to have e raised to the ln y is equal to e raised to the x squared plus c. Now let's talk about why we can do this. E is equal to e. So ln y must be equal to x squared plus c, which is what we have here. So it works, we can do that. Now it turns out that e raised to the ln y, the base of the natural log function is e. This simplifies to y. Now, how can we simplify that expression? Review in algebra, we know that x squared times x to the third is x to the 2 plus 3, which is x to the 5th power. So working in reverse, let's say we have x raised to the 4 plus 5. We can write that as x to the 4th times x to the 5th. So e x squared plus c can be written as e to the x squared times e to the c. But I'm going to write this one first. So we have e to the c times e to the x squared. E is a constant, c is a constant raised to a constant is a constant. So we can simplify our answer like that. Just so you know, this c is different from that c. They're not the same, so you can think of this as lowercase c and maybe that as uppercase c. Now let's plug in our initial value. Y is equal to 3, x is equal to 0. Anything raised to the 0 power is 1. So therefore c is equal to 3 in this example. So the solution to the initial value problem is 3e raised to the x squared. And so that's it. So now you know how to solve the initial value problem as it relates to differential equations.
Nick, I'm just looking at you now. Like, how tall are you? You look like you're, what, 5'5", 5'6"?
5'7", the inch.
In this video, we're going to talk about
Okay, we already remind you about the differential equation, yeah, differential equation. So I would like to stop this the sound, and I would like to remind this, yeah, repeat this. Okay, up to now, yeah. Up to this step, actually, that the problem is what? Okay, where is it's not easy to. Okay, let's check. Here is the Okay. This is the problem that we have. So y dot equals to 6x minus 3. Yeah, minus 3 here. So y dot equals to 3. So the problem is this one. So the question is that what is y? Y equals to what sign? Because this is the differential. So we have to finish this one. Of course, we try to integrate of this one. Yeah. First by using dy over dx. Yeah. And then equals to 6. Yeah. 6 minus 3. And then we multiply all of this. Put into this by dx. Yeah. Dx for dx here. Dx and dx. So anything that dx is not 0, so you can multiply this equation. Yeah, this equation for the first equation, this one, and then apply this one. Yeah, so that you can cancel out this one. Yeah, so dy equals to 6x dx plus minus, yeah, minus 3 dx, yeah, and then you integrate all this. So integrate dx dy plus to integrate 6x dx minus integrate 3 dx. Yeah, okay, and then you'll find integral dy of course y. Yeah, integral of sec mean since x squared for 2, yeah, dx here, yeah, up so dx to, yes, x here minus 3x minus c, yeah, plus c is okay, plus minus c is. So you have to find out this one, but in the problem there is a there's a number, or for example, if y equals to x equals to 0 is what? For example, is d, for example. So you have to find out that there is an initial value here. Yeah, this is initial value. That's why this program here is initial value in the differential equation. Because if you have a differential equation, so you have to solve by using integration, yeah, to find out the y, yeah, because the problem is in this one, yeah, dy over dx. So you have to find y, yeah. Maybe this is non-linear, yeah. Maybe this is non-linear. Maybe d square x over dx square, for example, yeah, yeah. Like in the problem of eigenvalue, yeah, you have second order, yeah. So this is square because there is a acceleration in it. Yeah. Okay, so this is that I try to explain about what Mr. Who is this and this sources that I use it. Okay, let me clear it. Support this one, and I try to here, because you know that there is a initial value. What is initial value? Yes, this one. This is the initial value. Whenever x equals to 0, mean y equals to 4. Yeah, because this one means that one. Yeah. Okay, so this is, you have to find the initial value, because you will be later for solving the c. Yeah, c is the constant that there is okay here. For differentiation, no problem, because constant become 0. But in differentiation and in integration, if 0, for example, plus 0, if you integrate 0 here, yeah, it will become constant. This is the problem. Yeah. So if, for example, you integrate x plus 0 ya, 0 for example, plus 0 for example ya, dx mean you have to integrate x dx plus integrate 0x 0 ya, dx. So you will have here for x square plus c. This is the problem. Yeah, this is the problem. You have to find c. C number is the constant. Yeah, plus c. So this makes the problem become initial value. Need initial. Yeah. For example, if you try to integrate the equation of this to become, for example, integration become that one maybe, yeah. But you need the initial value here, c, yeah, c here. Maybe, of course, for before you y equals to x, for example. But if you integrate, yeah, integrate means integration of y dx equals to integral x dx, yeah. So we'll find out that this is for half x plus c. This one c. Yeah. So you need initial value to solve this one. Okay, yeah. Okay. You focus of this. Try to write down initial value. Initial value in your chat room. Initial value. Okay, initial value. Yeah, clear out. So you already know about the first problem. Yeah, first problem is this one. Of course, first example. Okay, I'll try to speed up this record. Yeah, this record. So if you solve this problem, so you can see that you would like to have before become 4 because you put the apply the initial value problems. Yeah, initial value itself. Okay, let me continue. So about the second one here, because there is a in the right side there is also y. Well, we have to find y. Yeah, we have to find y. What is y? Yeah, yeah. So the problem is y is what? This is also y here. Yeah. Okay. So to solve this one, we have to have the strategy. To find out this one. Yeah. There's a strategy that will now about the strategy of this one. It's about okay, let me continue. Yeah, there is an initial value in the right side here. Yeah, x equals to y0 is equals to 3, for example. Yeah, if this is y equals to x equals 0, y this one. So the procedure almost similar before. Multiplied by dx, yeah, multiplied by dx here. Yeah. That can cancel out. So you will find this one. Yeah. Okay, yeah, we integrate also both sides because now we have this is the make us the problem more. This one, yeah, it's over y. This one over y. Okay. Okay, let's continue and then. So the integration of integration of y dy equals to L and y. This is the solution. So if we differentiate dln L and y, dl and y over dx, so we'll have over y here. So for y mean the integration of this one is L and y. Yeah. So we continue. Yeah, this is to x equal to the power of 1 and c. Yeah. So there's always c here. Always c here that we would like to solve. So that way we need the initial value problem, initial value number or initial value itself. Yeah. You have already this one. Yeah. Okay, and we use the rule of this one. You say the rule. The rule if just remind you because this is comma if e point something, yeah, for example if p point x, e point ln x, for example, so become x, yeah, e for example ln x square per 3, for example, so become this one, x square. Yeah. This is very valuable, yeah? Very useful for finding any problem in engineering. Engineering is very important, yeah. Okay, let us continue. And then we continue using this, yeah, the rule of e power of something, yeah. We have the power of something, for example, just ex squared plus c, yeah. This one, yeah. If we have a power 2 times x plus 3 mean x2 power 3, so x squared plus c mean e equal to this one, yeah. X squared mean e x squared plus e power c. Yeah. Okay, so please focus on the target that we have to finish to c, the number of c. Yeah. Okay. Okay. And then just for the continue, we just apply the initial value. Yeah. How to find c? Yeah. Just put, yeah, because we have if y x equals to 0, 3, c a by 0. So 3 equals to c x 0, 1. So c equals to 3. That's all. Yeah. This is the solution for exact value, yeah, for exact procedure. Yeah. But how about in the non-exact procedure? Okay, there is also explanation here. Yeah, from Stanford University. We try to have this, the sources from Stanford University, but this is useful. Yeah, it's very useful. So if you have a numerical differentiation using numerical and use the forward difference formula, so if you try to find out the differentiation, differentiate something, yeah, so you will have this one, yeah. This is 8 x or delta x yeah, this one delta y. So if y x0 is the solution here. So delta y here is this one. Yeah. This one. The numerator, yeah, numerator. This denominator is h here, because this is y x equals to just close, yeah, just approximation. Delta y over h, because h here identical to delta x. Here is identical to delta x. The horizontal differences. Okay, and because the focus of to find that y, yeah, to find the y, the integration itself. So we have to continue for the next page here. So the finding of this procedure is to find the here the one. So how to solve, for example, here, yeah, this one and here. If you know this one, yeah, y for x0 here, yeah, so you have the position here, yeah, by x0 here. So how to find this one? Yeah, find delta by using that one. Yeah. Okay. So this is look like that very very general. Yeah, it's not smooth, and still the number is not so friendly, and not so what we call it. It's very rush and many errors. Yeah, errors. It's very it's not smooth. So there's error here, of course. This is numerical computing. We deal with the error, how to minimize this error. Yeah, error. Yeah, because we only find this one actually that we look like to this target. Yeah, but using numerical computing, we have only find this one. So there is error here. Yeah, here is the delta x. Yeah, here is the delta y. So y dot mean delta y. Yeah, y equal to x. Okay. Yeah, we continue. So we deal with the how to minimize the error, because this error to become larger and larger if you solve the big or many time of steps. After increasing the steps number, you will have the greater error. And this is many mathematicians like Runge and Kuta try to solve by using a formula that they studied about that. So this is the approximation. Yeah, this is the approximation that we got. Y one is y here equal to this one. So there is error. Now, of course, this is plus error. Yeah, error. Plus. Yeah. Error that I saw you before in the picture here. Yeah, there's error. Error here. Okay, next, and then solve this. We try to have this one. Yeah. So therefore, the number of next step. Okay. The number of next step here, n plus 1, of course, yn is knowing, and then plus h, look like this is delta x, yeah, delta x, of course, this one. So this is just very, just only approximation, yeah, approximation. There's error, of course. Yeah. So this is the problem that we have, many error and error, yeah. And then how to solve it? For example, this one, x1 is this one, and x2 is this one. Yeah. So the error to become larger and larger, yeah. Larger and larger. So have to find out, and finally finally, one of the mathematician, yeah, and this one, yeah, this one, I try to have this one, yeah. Have a formula, yeah, formula. Yeah, this is very important. I give you this. I will give you. This is sources. I'll send you. Yes, this is just integration. Yeah, just introduction. Yeah, introduction. So anyway, I already introduced you as at least yet you know that there is a initial value problem, although it's not including in your topic for going to be examined. Yeah. Okay, and also for example, this one. Yeah. This I use this exact problem for using videos. Yeah, I use this sources, the source from the YouTube, and then for numerical problem I use Stanford University sources, and this is a approximate. Of course, this is maybe it's not so clear, yeah, but at least you know that this initial value problem, initial value, yeah. Initial value determine, yeah, or you know, yeah, determine, already have determine. And what is K? K is this one. This is by Mr. Rugan, yeah, because maybe this is two people, yeah, Professor Ruga and his assistant, maybe, yeah. So was very nice. So everything is numeric, yeah. So you give this is numeric, yeah. So after finding a K1, you have to put K1 is here, Y is here. So it's very nice, yeah. And then after finding K2, this is K2. Yeah. After finding K3 is here, K4 here. So mean that this to try to find out the solution become better and better, yeah. So Y I plus 1 or N plus 1 later, yeah, we predict the side, yeah, for example, and then we'd like to see here. So using this one, yeah, this is why I, yeah, this is why I plus 1, yeah, yeah. So this one plus, this is over 6, right? This one, yeah, here, K1, K2, etc. Yeah, it's very nice, actually. Yeah. Okay, yeah, and then you will see that this make or life in to solve the differential equation problem. It's very become easier, become simple. Okay. Yeah. So actually, that if you find out this form, for example, is this one. You would like to find the target is here. Yeah, but you only find this one, and y x1 is here, yeah, y x1 is here. Should be like this one. So the error is this, of course, it's very error. This is error. Because this should be here, but we find only here. By using Euler method. This is very simple method. Yeah. Very simple method using Euler. So if the problem is linear, close to linear will be better, but as increase the non-linearity of the equation, so the solution to become, the error of the solution to become greater, yeah, greater and greater. Okay, next, for example, this one by using Euler method, yeah, by using h different, h mean at the delta x, yeah, so the increment becomes small and small to become closer to the true solution or exact solution. So the exact solution is in the bottom, yeah, the bottom. So the lowest position here is exact value. So become h or delta x to become smaller. Yeah, this is also h. Yeah, to become smaller and smaller. So will become accurate. Yeah, if you use the x become greater, of course the error become greater too. Okay, next. Okay, if you use Yogyakarta here, yeah, then look like this one, and then someday, yeah, there's a correction. This is very good. Yeah, here method is look like that second order Yogyakarta. Yeah, so in order to have we only having the side, yeah, the side they have a second correction. So as before we have only this one, now we have correction here. So the error before is this one, yeah, 0 here to become smaller because there is a correction here, correction of the slope of this tangent lines. Harus singgung ya, as correction. Okay, next there is a of course there is a correction and correction, yeah. So the Yogyakarta of course this is the last one, yeah, the last one. Here is the third order. Third order mean there is a 3 correction, yeah. There's correction 1, correction 2, correction 3, yeah. This one. There is a correction. The bigger correction, of course, this will be better, yeah, will be better. So here, if for example, finding the different formula using analytical, exact is here one, yeah. Using Euler is this also, yeah, or the exact is this one, yeah. Exact is this. Exact is this one, yeah. This is analytical or exact. Yeah. Analytical, and Euler is this one, yeah. This is if we use the numerical component, this one. If Yun, and there is many methods, yeah, midpoint, Ralston, etc. You can find the discussion. Of course, using Yogyakarta is very closer for the order 4. Yeah. Okay, yeah. So that's for this the problem here. Yeah. Okay. Right then. Okay, for your fourth rolling call. Okay, I done. Okay. So okay, and then for next step, you have to find the classwork. Yeah, you have to find classwork. But you see here that the classwork is in the not initial value problem. Yeah, but still the most important that will be one point to know that is eigenvalue. Yeah, so eigenvalue for the second for the 2 degree of freedom you absolutely should know well. Yeah, we know well because it at least one equation is very important. It's not you cannot pass it problems on the eigenvalue for 2 DOF, yeah, 2 degree of freedom system, so will fail the examination. So it is better you try to solve this one. So I would like to upload from the problem here before I send you for in Google Classroom. I'd like to share here, yeah, to share a better for your homework. Yeah. Is on the classwork, yeah, classwork. Here is in the setting you could download. Now it's still running. Okay, yeah, you can download in the setting room. Yeah, you could download. You need more explanation. I send you also an explanation, but I'll also send you in the Google Classroom. Yeah, Google Classroom. Okay, get ready and then